We are going to learn today how to solve systems of simultaneous equations using the substitution method. We looked in the previous lesson of a system like, for example, y equals 3 minus x, y equals 2x plus 1. We saw how these two equations represented graphically are lines, and in order to find x and y that in the same time verifies both equations, I'm looking that this y is the same as that y, so I can write therefore that 3 minus x must be the same as 2x plus 1 because both of them are equal to the same y. So now I've got a linear equation with one unknown, x, so I need to find x. I add x to both sides, so I get 3 equals 3x plus 1, subtract 1 from both sides, therefore 2 equals 3x, or 3x equals 2, I always like to have x on the left hand side, and then I divide both sides by 3, so I get x equals 2 over 3. I need to find y, so if I replace in the first equation, so replace in, doesn't matter in which I replace, but the first one looks easier. Y is 3 minus x, so y is 3 minus, and x was 2 over 3. Therefore, y equals 7 over 3. So my solution is x equals 2 over 3, y equals 7 over 3. As we saw before, this is a graphical representation of the two equations. So, as you see, this line has a negative gradient, so it must be y equals 3 minus x. So this one is y equal 3 minus x. The gradient is negative 1. And the other one has a positive gradient. This must be y equals 2x plus 1. Also, you can see that the y-intercept for this one is 3. The y-intercept for that one is 1. Now, there are many points, just revising a bit what we've done last time. There are many points where y equals 3 minus x. For example, x equals 1, y equals 3 minus 1, 2. X equals 1, y equals 2 is that point. Or x equals 2, y equals 1, x equals 2, y equals 1 is that point. Or x equals 3, y equals 0. See, 3 minus 0 is 3. So x equals 3, y equals 0. And that's another point, and so on. But none of those points verify the second equation, because I want in the same time y to be also 2x plus 1. So see, if x is 1, here y will be 2 times 1, 2 plus 1, 3. So if x is 1, on the second line y will be 3, is that point. So they are not in the same time. That's why I'm looking for a point that verifies both equations, is on both lines. And my point given by GeoGebra is 0.67 to 0.33. Now, if you put these two fractions in your calculator, you see that they are exactly these numbers. These numbers are rounded. So this is a solution to this system. We just revised a bit what we've done last time, and now we are moving to the next slide. Let us now assume we want to solve the following system of linear equations. X plus y equals 6, 3x minus y equals 1. It is very similar to the previous one, just y is not subject to the formula. In the previous one was written as y equals something for the first equation, y equals something for the second equation. I could do the same here, but the equations are going to get increasingly more complicated, and I want to reduce the number of algebraic operations I'm doing. So if I'm to still want to use the following method, I will start with the first equation, x plus y equals 6. So if I want y, I will need to take away x on both sides. Therefore, y equals 6 minus x. From the second equation, I need to do the same. Because y is negative, I will add y to see it on the other side with plus. It's easier rather than working with negative numbers. So 3x equals 1 plus y. And now I just want to have y on the right hand side, so I take 1 from both sides. Therefore, 3x minus 1 equals y. So now I have these two equations, and it's very similar to the previous one. Therefore, I can write from the two equations, I can write 6 minus x equals 3x minus 1, because both of them are equal to y. And I have one equation now with one unknown. Add x to both sides. We learned in the previous unit how to solve such equations. Therefore, 6 equals 4x minus 1. Add 1 to both sides. Therefore, 7 equals 4x. Divide by 4 both sides. So x equals 7 over 4. Next step, we have replace, because we want to find y. Replace or substitute. X into any of those. Probably the simplest is y equals 6 minus x. It's in pink. That's how it gives me the relationship between x and y. So I get y equals 6 minus 7 over 4. Therefore, y equals 24 over 4 minus 7 over 4. So y equals 17 over 4. So my solutions are, we need to put them together. X equals 7 over 4, y equals 17 over 4. I can again check with GeoGebra, which I'm going to do later. But now I'll show you another method which is practically the same as this one, just rewritten a bit different. So see, this one is called substitution, because I substitute this y into that equation, the second equation. So from the first equation, y is the same as 6 minus x. So I substitute, instead of this y, I'm substituting 6 minus x. That's why it's called substitution. What we have done on the first slide is still the same as this one, and it's still called substitution. See? So I'm going to show you another method to solve the same system on the next page. Same as before, see, the same system. I want to substitute y. Therefore, if I take the first equation, x plus y equals 6, I can find y, of course in terms of x, by subtracting x from both sides. Therefore, y equals 6 minus x. Now, I do not need to find y from the second equation, and I can substitute this y into the second equation. See, why would I make y subject to the formula? I just substitute it. So the second equation, let me copy it here, becomes, this is a second equation, 3x minus, and then I substitute this y with 6 minus x. Remember, you need to take away the whole y, so you need brackets, and equals 1. So see, this one was my previous y. This is a substitution step. Now I open the bracket, so 3x minus 6 plus x equals 1. Therefore, 4x collect like terms, minus 6 equals 1. Add 6 to both sides. So 4x equals 7. Divide by 4. Therefore, x equals 7 over 4. Now, substitute or replace x into Probably the simplest is y equals 6 minus x. Therefore, y equals 6 minus 7 over 4 is the same as before on the first slide, so we get 17 over 4. So my solution is x equals 7 over 4, y equals 17 over 4. I'm going to show another method of the same. For example, from the first equation, I want to substitute x. So if I want to substitute x, I will leave x on the left hand side by taking y from both sides. So I get x equals 6 minus y. And then I substitute this x, into the second equation. Into the second, and the second was 3x minus y equals 1. So see, this x, which is 6 minus y, is the same as this one. So my second equation becomes 3 times, and my x was 6 minus y equals 1. Open the brackets, 18 minus 3y minus y equals 1. Therefore, 18 minus 4y, collect like terms, equals 1. Add 4y to both sides so that I work with positive numbers. Therefore, 18 equals 1 plus 4y. Subtract 1 from both sides. Therefore, 17 equals 4y. Divide by 4. So y equals 17 over 4, see, exactly the same as on the previous slide. Now substitute or replace y into x equals 6 minus y. Seems the easiest one. Yeah, I can use any of these, but this one seems the easiest one to find x. No matter where I replace y, in any of these I should get the same x, so it doesn't really matter. So x equals 6 minus 17 over 4, 24 over 4 minus 17 over 4, so x equals 7 over 4. Same, of course, same answer as before. So my solution is x equals 7 over 4, y equals 17 over 4. You know that I can write my solution as a point in the coordinate system in this order. This one, the first one is x and the second one is y. It's another way to write the solution. I can always check with GeoGebra. Now on my last slide, I'll take another system of simultaneous equations. X plus 2y equals 6, 3x minus 4y equals 8. If I want to use the substitution method, the idea is which unknown am I going to find to substitute. I will not find y from the second because finding y will involve fractions. Let's try. X plus 2y equals 6. If I want to use y, I need to leave y on the left hand side. So 2y equals 6 minus x, and now divide both sides by 2. Remember, you need to divide the whole right hand side by 2, so I get y equals 3 minus half x. And see, I don't really like it doesn't matter, I can now replace y, it's correct here. But if I don't want to work with fractions, then I should plan better and find x from the first equation because it has a coefficient of 1. So I'm going to leave this method. Yeah, it's correct, but it's not the easiest. And looking at the first one, I will find x by taking 2y from both sides. So x equals 6 minus 2y. And now I will replace this x in the replace or substitute this x into the second equation. Yeah, so I have 3 times x minus 4y equals 8. Same second equation. Open the brackets, 18 minus 6y minus 4y equals 8. So 18 minus 10y equals 8. 18 minus 8 minus 10y equals 0. I subtract 8. 10 minus 10y equals 0. So 10 equals 10y. Y equals 1. Yep. Substitute y into here. So x equals 6 minus 2 times 1. So x equals 4. So my solution is 4, 1. I can check with GeoGebra, or I can just check, say, and that's the same in all my answers. I can check in the system. So if I replace x and y here, x plus 2y must be 6, and in the second one, 3x minus 4y must be 8. So if I check, I have x plus 2 times y equals 6, correct. And in the second one, I'm going to have 3 times x minus 4 times y is 12 minus 4, it's exactly 8. So my solutions are correct. The idea here is therefore you need to plan a bit, and if you want to use a substitution method, look which of the unknowns it's easier to substitute, and in this case is x because it has a coefficient 1.